So hi everyone, welcome to our event. This event is brought to you by Data Talks Club, which is a community of people who love data. We have weekly events and today is one of such events. And yeah, if you want to find out more about the events we have, there is a link in the description. Check it out. You'll see all the other events we have in our pipeline. For example, there is a workshop about prompt engineering that happens quite soon. Then do not forget to subscribe to our YouTube channel if you want to see future streams like the one today. And we have an amazing Slack community where you can hang out with other data enthusiasts. And I'll post a slider link. This is the link that you can use for asking questions. So Arman will now give a presentation, and after the presentation, there will be a part with Q&A. And this is when we will cover the questions. So that's more or less it. So now the floor is yours. Please share your screen and let's get started.
Absolutely. Thank you. Very excited to be here. Okay. Can you see the slides?
Yes.
Okay. Awesome. So the title of this talk is The Art of Choice, Simplicity versus Optimality. But the first question is, why do we call this art? Well, most of the discussion that we will have today, you will notice there is no right or wrong answer. It's not necessarily data-driven decision-making, and it's not necessarily evidence-based. There's so much contextual understanding, intuition, and human judgment involved. That's why I think it's on the border of science and art. The topics that we will discuss today is assumptions that we make in real world. Sometimes we are aware of the assumption we are creating, and sometimes we just forget that we have those assumptions. We will talk about adaptability of the designs of algorithm that we propose, as well as the agility that we care about and how much agile we want our team to be. And we see how the design of algorithms that we select will impact that. There are also many other considerations that we will discuss, and hopefully we will continue talking about those in the Q&A, because I really want to know how you think about the other constraints and consideration that I won't be covering in this talk. So let's start with the assumption and redefining what optimal really means in real world. Starting with a simple rideshare example, imagine that we have one car and two passengers that are looking for a ride. We know the ETA to the one in the north is 205 seconds, and the one to the south is 217 seconds. And the question is, what should be our decision? Which passenger should get the car in this example? Well, I think this is an easy problem. We know the ETAs, and with the amount of information that we have, it's best to assign that to the rider who has the shortest ETA. Because if we are going to only fulfill one ride, at least we are fulfilling the one that has the shortest ETA, and one rider get the ride faster. But is this the optimal response that we can have here? What if our ETAs are inaccurate? We were assuming that the numbers that we are seeing are the accurate ETAs. Now, what if we relax that assumption? Should we still assign the car to the rider in the north? What if we spend few months, create a much more advanced model on predicting the ETAs by considering a ton of real-time signals? Then we might learn, oh, our ETA was not that accurate. The ETA for the north is 235 seconds. The one in the south is 210 seconds. So in this scenario, we learn, actually, we will minimize our ETA if we dispatch or assign this car to the rider in the south. And the next question is it optimal now? Now, what if we relax another assumption? We were thinking about ETA. We were assuming that optimal in this real-world example is minimizing ETA. But why did we make that assumption? Why did we think that minimizing ETA is the most important thing that we can do here? What if these two rides are not equal to each other? What if one of them is a 34-minute ride The other one is an 18-minute ride. Well, from driver point of view, they want to be busy. They don't want to stay in a status without having any ride. Therefore, having longer rides increase their utilization. So it's better for the driver to have the longer rides. As a result, it's better for rideshare companies to give drivers what they want more because their benefit is aligned with our benefit. So should we assign the 34-minute ride here or the 18-minute ride, even though their ETA is a little bit different? I think the answer is obvious. The 34-minute ride is the right answer here. Now, what if the 34-minute ride goes to a suburb? That after a driver drop off that rider in the suburb, there won't be any chance of getting another ride. And that driver needs to probably drive all the way back without any passenger. While the 18-minute ride is going to a downtown, which is full of potential ride requests, and the driver can immediately get another ride. Now we are relaxing the assumption of only looking at the next immediate ride, looking at the longer term future. Now in this scenario, why shouldn't we assign the 18-minute ride? That sounds more optimal or more efficient. Again, we can relax those assumptions as well by considering other realities, like what if the gas that the car has is low and they're needing to find a gas station, and there is a gas station beside the destination of the 34-minute ride, while the other one is in downtown, it's a busy area, there is no gas station, so it would be very challenging for the driver to find a gas station. Now the optimal answer has changed. We think the 34-minute ride is the best answer. And we can continue this again, and again, and relax our assumptions, so on. We might even conclude that maybe we should do nothing right now. We should wait a little bit because there might be a chance that a much more interesting or valuable ride will become available beside the current location of driver in less than a minute. So as you notice, as we add to the constraints, as we relax the assumptions that we had, our optimal solution changed. So optimal, in this real-world example, was a function of our assumptions. Now, looking at all the assumptions that we had, and many other assumptions that we have and we haven't added in this slide, we can trade off how much important is relaxing those assumptions versus making the current model within those assumptions more accurate. Now that we know how many other considerations we were missing by just focusing on ETA, the question is, was it a right investment to spend months of data science works on improving the accuracy of that ETA model by a few percentage? There is no right and wrong answer here. It very much depends on the context, but at least, maybe not. Maybe working on relaxing some of the assumptions that we had would gain much more value compared to making the current model more complex or increasing their accuracy. Another important aspect is adaptability. How much do we want our models to adapt themselves to the reality in the future? Is our environment dynamic or static? Let's have two more rideshare examples. Let's start with this one. How to calculate ETA for queued ride. But what are the queued ride? Imagine a driver that has a passenger inside the car, and they are very close to the drop-off location of the passenger. And there is another rider available very close to the drop-off location of the current rider. So in that scenario, it sounds very efficient to queue that rider to the list of rides that that driver needs to complete. So the driver, after dropping off the current passenger, can go and pick up the next passenger. In this scenario, what would be the ETA that we show to the next passenger? to the passenger that will be picked up? Well, there are three components here. The first one is the ETA to the drop-off location. Then the amount of time it takes for the rider to leave the car and driver start driving again. And lastly, the amount of time it takes to go from the drop-off location to the pickup location of the next passenger. In this example, let's assume we know the ETA to the drop-off location and the time it takes from the drop-off location to the pickup location, 60 seconds and 90 seconds. The question here is estimating how much it takes for the rider to leave the car and for the driver to start driving again. Now, let's have a few different designs. The simplest solution. How about we consider a fixed value? Let's say calling that it takes 1 minute, or it takes 10 seconds, or any other number. I don't think we can come up with any simpler solution than that. But that might not work well. Different rides, different situation might have very different time requirement in order to leave the car and have the driver on the road again. What if we add a little bit to the model, making it a bit more accurate, but still very simple? For instance, separating airport rides with other rides. Because in airport rides, most passenger has luggage and they need to go open the trunk of the car. It takes additional time. So what if we decide for a fixed number for all non-airport rides and another fixed number for all airport rides? Well, this sounds decent, but it's still very simple. Alternatively, we can make a more complicated model, which hopefully will be much more accurate. For that, we can consider drop-off location, pick-up location. For instance, if the rider or customer is coming from a shopping center, they might have some items in hand, so it might slow them down for going out of the car or coming inside the car. Maybe time of the day. Some drivers are kind enough that they stop at the night until the rider go inside their home, and then they leave. So that might impact that time. Number of people in the car, whether it's a snowy or the weather is really good, it impacts how fast the rider can leave the car, and many more features. Now, we have three potential designs here, and the question is which one we should use. Let's imagine we go with the second model. We do an experimentation, and we notice that by using this simple model, experimenting that over 2 weeks, we noticed everything is fine, and we think the model is good enough. And again, what is good enough is another question, which requires that human judgmental call. But assume that we know that it was good enough. Now, is this the right choice? Should we go with this model? How much do we expect the time that rider takes to leave the car changes over time? Does it have so much seasonality, or is it kind of a static? I would say it's kind of a static. There might be some seasonalities based on like winter and summer, but I don't expect it to change so much. So if it's working well during the past 2 weeks, it's fair to assume that it will work well for the rest of the year as well. Now, let's consider another example. How to determine prices for the riders. Again, let's have multiple designs here. The first design, which is the simplest solution, one of the simplest solutions, let's imagine rate card system, similar to taxi systems, that you pay as you go based on the mile or kilometers and the amount of minutes that you're inside the car. But there is an issue with that. Let's imagine we experiment this idea. And we notice that we are not reliable at the times that demand is much more than supply. Then some of the riders who really need ride are unable to find a ride at those times because we just don't have enough supply. Let's imagine we analyze the data and we notice almost always during the evenings, the demand is much more than the supply. So we improve our model and we define two sets of rate cards. one rate cards for regular hours and one rate card for the evenings, which is higher than the regular rate cards. So it's kind of balance the demand and supply. We experimented that again for around 2 weeks, and we noticed, oh, this is great. We don't have that reliability issue anymore, and this solution is good enough. The question is this the right solution? Should we go with this one? And if we want to do that, what kind of question should we ask ourselves? For instance, we should ask, is the pattern of supply and demand static or dynamic during the year? Some of the examples are, is the pattern of demand and pattern of driving hours changes during summer and winter? How about the special dates like Halloween, New Year Eve? How about much more significant changes in our lifestyle like COVID and pandemic? How about special events such as Super Bowl, Formula One, or any other event that require a significant number of demand or completely changes the distribution of ride requests? Looking at these, it sounds like it might not be the right solution. Like, we will have that reliability issue the first time that we have a special date or we have an event, because that event might be in the morning. We still might have many more demand compared to the supply. And our design prices are not able to balance the system. So with this consideration, we need to answer the question, is this solution good enough? Do we want to make it more complicated to be able to adjust itself to these dynamic environments? Or are we okay with a simpler solution, knowing that it has cost of reliability on some specific events, special dates, and anything regarding seasonality? Again, there is no right or wrong answer here. These are just different trade-offs that we need to make. How about agility? Let's have another rider example. Let's imagine a rider opening up their app, and we need to show them how soon we expect them to have their driver after their request. These are the ETAs that you will see inside the app. Whenever you open any of the rideshare apps, you will see, for instance, opening Lyft, you will see how far the driver is. It can be 2 minutes, 3 minutes, 4 minutes, or any other number. But how can we predict those numbers in general? This is a really hard problem to solve. There are many considerations. Let's start with explaining some of those. First, there are multiple drivers available around each rider. And the rider haven't even requested yet. So we need to have some idea which driver will be assigned to the rider after the rider requested. But why is that challenging? Because there are also other riders around that just requested or haven't requested yet. So we have contention with other passengers. Now we have a network that we need to decide or predict which driver will be assigned to which rider. Aside from that, we don't even know where exactly the drivers are. We have the GPS signal, but that's noisy, that's not accurate all the time. And aside from that, drivers are driving around. When they don't have a passenger inside them, they are not just sitting in one location. And when they are driving, it's really hard to predict which way they will go when they reach the next intersection. So with all these complexities, we need to design a model to tell us what is the expected time for this rider to get a driver. Let's have different designs. Let's imagine we create a black box model without knowing what we put inside, probably too many features, like whatever we can see. We put all the inputs, and as the output, we get the ETA that the rider will have. This is a pretty decent model. Like, the size is manageable. We expect it to have a really good accuracy as well. How about another model? Let's separate that into two distinct models. In model 1, we estimate or predict which of the drivers we will end up assigning to the rider. And model 2, try to estimate what would be the ETA of that driver. How can we trade off these two designs? What are the parameters that we need to think about? I can't imagine myself even thinking about design 2 when I was a student working on optimization all the time, because we know that model 1 is giving us a better accuracy. There is no way model 2 can beat model 1's accuracy here. So higher precision is the benefit of design 1. But how about design 2? What is the benefit of design 2 over design 1? It's faster iteration speed. Let's imagine we create design 1, and then a team of data scientists works on GPS signals and made them much more accurate. Or another team worked on ETA estimates, improved the accuracy of estimates. Or the algorithm that assigns driver to riders get updated and change the logic. For each of these changes, we need to retrain model 1. Model 1 is designed to work with the current state of the world. But after these changes, every time we make a change, there is no guarantee that that model will work perfectly. And we need to retrain that. Now we can make that more complex, making it retrain itself. But that's another discussion. How about design 2? The nice thing about design 2 is that two independent teams can work on these two models. They are independent enough that if we just improve model 1, we are improving the outcome of the whole systems. We don't need to go and retrain model 2 at the same time. So given that we are removing the dependencies, we are removing the blockers for improvements, we can hope that we will have faster iteration speed in improving either of those models. These were just a part of considerations that we can have. There could be many more questions that we need to ask ourselves, or many other constraints that we should consider. Some of those are scalability. Why should we care about the scale? Let's imagine we are creating an algorithm for one specific problem, but we might want to scale that to use that for other use cases. Let's imagine we are working on some algorithm that predict the events. Now, we might want to use the same algorithm to predict the flights that are sitting at each airport. Or we might use the very similar model to predict some other metrics. So is it better to fine-tune a model to be very specific on one use case with the higher precision and accuracy? Or is it better to sacrifice some of the accuracy, but making models to be easily generalizable to other use cases? Interpretability and observability. This is one of the most important ones. We know most of the times we have unknown unknowns. There are things that we don't know to incorporate those in our model. So it's extremely important to have observability into the performance of our models. This is especially important when we are deciding between a black box model and a model that we can observe every piece of that. Sometimes there are other considerations that force us to have observability. Like sometimes we want to build trust. To build trust, we need to be able to explain how a decision was made. If we have a black box model, we can't say this is just the output, we think it's right. We want to be able to explain that. And these considerations significantly changes the design choices that we have for each problem. For some problem, we might not care as much about observability. The accuracy might be the most important metric that we have there because the impact would be so much on the business or on the performance. Next one is maintainability. When we are building a model, when we are selecting a design, We are not doing that for the next few days or next few weeks. We are probably going to have that design and that system for multiple months or years. So incident happens. We need to be able to debug the issue. We need to be able to know how the model works, be able to find the issues over time. Now, should we create an extremely complicated model that we need to have extremely senior scientists specialized on working on those type of models to always be there to fix those models anytime anything goes wrong? Or should we have a more generalized model that anyone can debug those if something goes wrong? How about retraining? Should we create models that are simpler, they don't require retraining over time? Or should we use more complicated models with the cost that they will be out of tune from time to time, and we need to retune them over time? Or should we even make the models more complicated and make them to retrain themselves? Again, the right answer depends on the context, and there is no right and wrong. Lastly, there are so many constraints. Every time that we decide to work on a model or on a problem, at the same time, we are deciding to not work on many other problems because we don't have unlimited amount of resources. Sometimes we have deadlines, and we need to create some feature, some model before some time. And those deadlines, those time constraints might impact our decision choice because we just might not have enough time to build some very complicated models. And lastly, it's cost. For instance, one can be computational power, the other can be licensing cost, or many other things that can impact our decisions. These are some of the trade-offs and considerations that comes to my mind. And I'd love to hear how you think about other consideration and what type of consideration you have encountered while trying to design systems and trading off between different system designs. With that, I would love to start the Q&A and know how you think about these considerations.
Yeah, thanks. So many questions, so few answers. So yeah, a lot to think about. And like, well, while you were talking about that, you asked at the end what kind of other considerations. What occurred to me is probably like also the maturity of the system. Like if we are at the beginning, if the project is just starting, or like it's been running for 10 years, like you would make different decisions, right? But how do you usually approach answering these questions? Like we can take maybe one of the questions is like, should we have a simple model that doesn't require retraining, or should it be more complex that does require? Like, how do you approach answering this question? Like, what kind of things you look at to arrive at the decision?
That's a great question. And that's a really hard question to answer because, as I said, there is no quite right or wrong answer here. Like, it's extremely hard to call one answer is wrong and then bringing training for that. But what matters most is making sure that we are at least thinking about different impacts that that decision will make on the systems. Like writing down what are the trade-offs that we are making. What are the pros and cons of each of the designs? For instance, one design will have more agility for the improvement for going to the next milestones. One design might take much more time to iterate on. One design will have a much better accuracy. We try to transfer that to the business metric, calling out what is the impact of that accuracy loss if we go with the simple model, and what are the benefits that we can get from those. Then presenting that in front of a larger group of audience to hear like how different people think about that, because there is judgmental call here. Gaining all the feedbacks, that would make it much more clear which would be the right solution.
And in terms of the process of making these decisions, so you said like one design might might promise good accuracy, another design like good agility. And by design, so you mean like proposed solution, right, in form of like a document with its trade-offs, pros and cons documented clearly in some sort of like, I don't know, document.
Yeah, by design, I'm suggesting about the solutions that we're suggesting for different problems. That can be different algorithms, that can be different amount of complexity, that can be different feature selection, approaches to solve that problem. And one additional aspect is that we don't have to have everything at once. So we might be able to like break down a problem into multiple milestones, starting from very simple ones, proving the concept, and then over time making it more and more complicated.
And in practice, how does the process work? So let's say we have a team or multiple teams that work on, I don't know, solving a problem, and then somehow, I don't know, senior data scientists or whoever in the team come up with different designs, right? And then somebody needs to decide which one we choose. Like in terms of personas and roles in the teams and the process, like how does it usually work in practice?
I think most of the time it's based on alignment. So you will have like a review meetings inviting every stakeholder, every scientist that have worked on similar problems or might have an opinion or being a stakeholder, having brainstorming on the approach, reviewing pros and cons together, hearing different feedbacks, having multiple iteration of improving the models, and hopefully at the end, you will have consensus on the approach that should be worked on.
But at the end, it's like, I don't know, it should be staff, data scientist, some sort of technical leader who should make the call that, okay, we're going with this solution.
Well, again, most of the times it would be alignment, but if in any case alignment cannot be made, sometimes the teams needs to make decision on the solution. So it is not role-based, it's team-based most of the time. Team lead, whoever those people are, they make the final call if alignment cannot be made.
And I'm also wondering, so one thing that occurred in my practice is sort of trying to go back to the past and understand why certain decisions were made. Like, for example, I don't know, for one particular problem, we decided there were multiple approaches and we decided to go with one particular solution for that problem. And then 2 years passed and then somebody comes and asks like, why did you decide to go with this solution? Like, weren't other solutions better? And then like all the people who made these decisions are long gone. They work in different companies. Like, do you somehow, I don't know, document these decisions, or how do you do this time traveling to understand how exactly this decision was made and like what kind of things were taken into consideration when making the decision?
That's a great point. I think that's a problem that every single company in the world has. Like, we become so focused on the things that we do, we usually don't focus on the things that we don't do. Like deciding on one algorithm, we decided we should not go with other algorithms, but the question is, are we documenting them as well? Like, are we documenting what approaches we have considered and why we decided to not go with any of the approach that end up selecting the current approach? I think documentation is the key here. And the more that we can make those documentation the structured way, like having formal reviews for designing the solution approach, and then having sections to write down, how did we end up in selecting this solution compared to like other possible solution, that can be a helpful approach to make sure in the future anyone can be on board. Some decision might be wrong, it's okay. The most important thing is that we will be able to improve our solution and our decisions over time. But without documenting those, there's no way that we can figure out why the decision was made and how to improve those in the future.
But then there is another trade-off, like, should we create process and make it formal? Because we can overdo it and make it too bureaucratic. or should we just, let it flow, right? Like, okay, let's do whatever, and then like things will work out magically somehow, right? So like there is trade-off between these two approaches. Like, how do we? I guess it's more like a rhetorical question. Like every company, every team needs to decide it themselves. But like I remember, sometimes for me personally, it was so difficult to actually force myself to sit down and like do all this documentation, because like there are so many things that wait for me to handle them, and like I'm sitting there and do documentation. It's like
Exactly, and
you need
that's
to be disciplined, right?
that's also very dependent on the size of the company. Like, are we talking about the 10 people company? Are we talking about the 10,000 people company or 100,000? So it has so many different features that will impact the decisions. But as you said, that's also another trade-off that requires judgmental call.
So see, we have quite a few questions. So the first question is from Adonis. So typically at this point, I share my screen, but since I'm from my phone, I will not do this. Hopefully you will be able to get the questions as I read them. So the question from Adonis is, thank you for a great presentation. I see we can have many assumptions and there could be new ones. How often we should run experiments to assess these assumptions?
Let me make sure if I understand the question. So the question acknowledge that we have the assumptions and believes that we know the assumptions that we made, so we are aware of the assumption. And it asks how often we should validate our assumptions.
That's how I understood it. Oh, yeah.
I don't think there is a general answer on how often we should do those, but I think it's important to do that at least once in a while, be aware of the assumption that we created and resizing the impact those assumptions might have. So it doesn't necessarily need to be experimentation. We can validate some of the hypotheses that comes from relaxing the assumptions with the current data that we have. And anytime that we think something has changed meaningfully, that might make those assumptions irrelevant going forward, we should go and test those assumptions again to make sure if they're still valid assumptions.
And is there like a good way of doing this? Like, I don't know, A/B tests or like other, or maybe I just talking to users.
Can you repeat the?
Yeah, like is there a way to assess these assumptions? Like, yes, there is experiments that we can run, but then like for me it's a little bit abstract. So I'm trying to like maybe think of a particular example how exactly we can assess. Like if we go back to your example where we talked about, the first one where like should we pick this rider or that rider? And we had some assumptions like the best ETA is the most useful one. And that, like when we were deciding if like we make a good decision, it was more like a thought process, right? So we just ask ourselves, like, we challenge these assumptions. And then at the end, we arrived at something very complex. But in practice, is it the only way to do this? Just challenge assumptions and then have some sort of group brainstorming sessions, or there are more like data-driven things?
Again, depends on the specific question. We might be able to have some data-driven approach to capture those automatically. And before like double clicking on that, I think a piece of the confusion here is that some of the assumptions are product assumptions. So like this topic is kind of on the border of science and product. Like what type of assumption we want to create as the proxy for the things that we build. Right. For instance, the first example that we have, we were focused at the beginning on talking about ETA, and then we relaxed that assumption as we go forward. Now, let's assume, yes, we believe as an assumption that ETA is a good proxy for the metrics of interest that we have. Now, we have pandemic coming on. the distribution of demand and supply and density and everything have changed within a few months. And now we can question, is it still the right proxy for the metric of interest that we have? For that one, we can have simulation. We have all the data, we can have different objective functions, we can solve them, and we can compare the results. Or we can have a parallel simulation to the production that always do that. And as soon as the results diverge significantly, we might know something has changed. So that assumption might not be valid anymore going forward. And that can be a trigger to reinvest time on those, think about the product that we built based on those assumptions, or the algorithm that we designed based on those assumptions. And if easy, going toward experimenting with some of those.
Mm-hmm. And another question that is related to like documenting past decisions. And it's like, how do you retroactively evaluate the impact of past decisions or products that were shipped? Is there a way to, because like we went, this is how I interpret the question. So we went with, I don't know, solution A, but there were solutions B and C, and we don't know, right? So what would have happened if we decided to go with, you know, B and C because we went with A?
So we usually don't have access to the counterfactuals.
Yeah.
Like if we select like option A, we don't know what would have happened if we go with option B. And another important piece is that we had some available information at the time that we made the decision between option A and option B. Now, 2 years after that, we might figure out, oh, it could have been better if we go with option B because of the new information that we have. It doesn't make that decision wrong 2 years ago, because with the valid information, with the available information at the time, the optimal answer would have been different from the optimal answer that we would have get right now with all additional context and information over time.
Yeah, makes sense. And then a question from Kedar, which still builds on top of what we discussed. Have you ever been in situations where a solution wasn't selected at the time, but later you thought, okay, that was actually the right solution, so let's reconsider it and come back to the like this solution B that we talked about instead of solution A and rebuild it?
Absolutely. That's the whole point of experimentation. Like, never be sure, so we experiment to make sure that our decisions are right. And every time that we fail on an experiment, we go and try to find out what we could have changed, how we can improve the solution, and redo the work until we got that right. So there is a feedback with the experimentation that help us to improve our, maybe let's call it that, incorrect decisions in the past.
So the key here is to have a clear metric that we can monitor to see the impact of the decision we make, right? And then if this is not great, or we expect it maybe better, then maybe it's time for us to think like, what would have happened if had we gone with like this solution B, right? And then we can try and just experiment and see what happens, right?
Exactly. And the result of that initial experiment that we ran, which the result was not favorable, but the data that we capture from that one is additional context to help us better design the solution.
And then again, I guess here, if a solution is simple, if it's easy to test, then maybe this is something we should prefer in some circumstances, right? Because like we don't spend a lot of time building the solution, then we test and then we see if we move in the right direction or not, and then we make it more complex in the next direction.
Exactly. And in addition to that, observability is usually more when the solution is simpler. So it would be easier to go back and see what went wrong, how can we improve that. So it's iteration and speed first, and second, observability. That suggests that at least for the MVP, it's usually favorable to go with simpler solution if we believe they can work. In some contexts, simple solution we know would not work. We need a very advanced model to be able to capture what we want.
And funny that this talk is about hailing services, because like on the way here to this stream, I used Uber. So in Berlin, we don't have Lyft, we have Uber, and then some competitors of Uber. And the model told me that I would get home by 4:47, which I thought, okay, like not ideal, but I'll still have like 13 minutes before the stream. And then of course I got in a traffic jam, and then there was another one. And despite all the attempts for the driver to like circumnavigate all these traffic jams, I still was a bit late. Yeah, so it's a very challenging problem, because like you don't know if there are traffic jams, like when you build this ATA model, right? Or like this data comes with delay, and then like there's no probably reliable way of capturing this data, right? So yeah, it's a very complex model. So yeah, luckily I was in time, but now I'm doing this from phone. It's a very fun experience. Well, at least I didn't need to to do it entirely from the car in a traffic jam. Yeah, that would have been funny. I need to get a bike. Anyways, thanks a lot for the presentation. So I don't have any more questions. Is there anything else you want to add before we wrap up?
No, I just want to thank you. It was a great talk. Happy to be here, and thanks for all the questions from audience. I wish I could see them as well, but like
yeah, sorry about that.
it's all good.
Yeah, well, that was a nice experience for me. So hopefully next time, yeah, I get more time to make sure like I arrive in time. But yeah, you never know if there are traffic jams. Anyways, yeah, thanks Arman a lot for joining us today, and thanks everyone for joining us today and asking questions. And with that, we will finish, and I wish everyone have a great rest of your day. Bye everyone.
Absolutely. Thank you.